Hey everyone, this is Ben Brandt. If you're watching this video, then chances are you've probably already seen my video on the solid wood dodecahedron here that I cut on my table saw. Now, as much fun as it was to put together this sort of fast-paced video on this project, I figured some of you might want me to slow things down a little bit and maybe go into more detail about how this was made, some of the decisions that were made along the way, and why. And this was just a really interesting project for myself in terms of design and making a jig. So we're going to get into a little more detail on how this was made. So stick with me and I'll show you how it was done. Thanks. So the first step in this project is to fire up Fusion 360, my 3D modeler of choice, and start building a 3D model of the dodecahedron that we want to make. Now I've set up a few parameters here. Mainly, one of them is going to be for the edge length of each face, and we'll talk more about that in a bit. Now, since the dodecahedron is made up of 12 identical pentagon faces, I'm actually just going to build out one of those pentagon faces, and then I'll assemble 12 of them together into the final model. So I've sketched out this pentagon, put a few constraints on it, set the dimension of one of the sides, and for this model I've got it set just to 1 inch, and we can tweak that later. Then we just extrude that up and give it a little bit of a thickness. Technically the thickness and the draft angle I've put on here don't really matter because that's all going to be hidden inside of the dodecahedron, but at least for assembling this thing together it's a little easier to see if it's got some thickness to it. And since this thing is going to be made of wood, we'll give it the wood appearance just so it looks nice. Now that we've got one of those pentagons built, I can start copying and pasting several of them into the model here, and we can start assembling them. Now it took a lot of tries and experimenting with Fusion to figure out how to assemble all these together, but it turns out I'm able to use a ball joint on all of the corners, the vertexes that meet on this model. Even though there's nothing spherical, there's no ball and socket joints, if I just put that ball joint on a single vertex, it'll allow me to join all of those points together and then just sort of fold it up into its final shape. But I join each of these pentagons together at the 2 points where they connect. And then to fold them up together, I just keep joining them by all of the points that meet. So I've got the bottom half of the piece all assembled, and now we just repeat this process again, copying and pasting 5 and then a 6th pentagon, and just assembling them together with those ball joints on all the corners. Now at this point we've got a working model of a dodecahedron, and we can start taking some measurements on it and adjust it to what we want. So here I'm taking a measurement from one face to the opposite face, and it turns out it's about 2.22 inches, which is really close to the 2¼ inches that I'm going for. If I'm going to be sticking 3 3/4 inch boards together, I want this thing to be 2¼ inches tall. So if we do a little math here, if I increase this thing by about 1%, that should give us the height we want. So I'll take my edge length on the pentagons and change that from 1 inch up to 1.01 inches. And by increasing that edge length by about 1%, that'll increase my overall height by about 1%. And now the model has changed very slightly, but if we go back and take another measurement from one face to the opposite face, it'll come out to 2¼ inches, right where we want it. We can also use our 3D model to figure out the overall size of the stock that we're going to need to make this piece. So if I switch to an overhead view, I can take a measurement between the two outermost points, and it comes up to about 2.8 inches. So if I get a block that's, say, 3 inches wide, that should give us enough material to work with. But rather than just make an assumption about the size that we'll need, we can actually model that 3-inch by 3-inch block of wood and see if it actually encloses the entire dodecahedron. So we'll add another component to our model, sketch out a 3-inch by 3-inch square, and then extrude it up to the full 2¼ inch height. And we can see that it does completely enclose our shape, and that should work out great. And now we know that we need a 3-inch by 3-inch by 2¼ inch block to make this shape. To make those blocks, I just took a 1x4, cut it into 3 pieces, and stacked them up. Add a little bit of glue and some clamps, and a little while later you've got a nice 2¼ inch thick piece of stock that you can cut down to 3-inch by 3-inch squares. Now you could certainly do this with a thicker piece of material, but I had a hard time finding anything thick enough that I could work with. And 3/4 inch material is pretty easy to find. But if I could find some really nice hardwoods in thick enough pieces, I think that would look really nice. Now this dodecahedron shape, you may recognize it as the standard shape of a 12-sided dice, or 12-sided die. But this shape in particular is one of the 5 what are called Platonic Solids, in that every face is exactly the same, every edge is the same length, and every angle is the same angle. So virtually everything all around this dodecahedron here is identical. So if I can figure out how to cut one of these faces, I can do them all. Now what makes this shape in particular easier to cut than you would expect is that the top and bottom are both flat faces, so if I can clamp it in place vertically and spin it around to cut all my angles, that's all I need to know. So if I can make this angle here, it's called the Dihedral Angle, the angle between every 2 faces. If I can cut that angle, I just have to fixture it in place and turn it 1/5 of rotation all the way around to get each and every face just right. Now, cutting the angle is actually probably the easiest part of this process, and probably easier than you would think. For the first prototype of this project, I actually just drew up that angle and printed it out, took it out to the garage, and took out my bevel gauge here and adjusted it to match the drawing on the paper. Once I had that angle set on my bevel gauge, I could then take it over to the table saw and adjust my blade to match the angle of my bevel gauge. And that actually worked really well for such an exact angle. However, moving forward, I decided to spring for the digital angle gauge that you see here that I've been wanting to get for quite some time. And it made the process quite a bit easier. And if you're interested in getting one of these for yourself, I will include a link to the digital angle gauge down in the video description, along with some of the other tools and supplies that I used here. First, I set up the saw blade to be 90 degrees from the tabletop, and zeroed it out, and then set it to be another 26.5 degrees off of the vertical. So that gave me the 116.5 degrees that I needed to make that angle for the dodecahedron. Now once I had that angle set, I needed a sled, a jig, to hold the piece so I could slide it through the saw. So we took a 1/2 inch sheet of plywood here, set it up with a 3/4 inch wide runner, and I glued that in with a little bit of CA glue to hold it quickly, and then some wood glue to give it some strength over time. Once I had that sled put together, I could then run it through and cut the one edge to that 116.5 degree angle that I had set on the saw. And the reason I cut that angle into my sled is that gave me a point to measure from for the location of the center pin. Now the first version that I made of this, I actually had to drill a hole in the bottom and the top here so I could put it on the peg in my jig, but that left a hole in the finished part. So I added a 1/4 inch piece of MDF on the top and bottom, which you may have seen in the video, and put a hole in that. And so I built up the shape here to include the top piece and the bottom piece to work out the dimensions for my jig, so that I could cut everything away and then remove those sacrificial top and bottom with the holes, and I'm left with a nice clean surface here on the finished part. So the top and bottom pieces, the sacrificial sort of MDF pieces that I put on there just for locating it on the jig, I drew out that square plate, printed it off at full size, cut it out, and then transferred those lines to the wood. And all I did was just poke a hole in the center and mark some holes at 5 points around the circle and just connected them with pencil lines. That was enough, and made a whole bunch of tops and bottoms for all of my pieces that way. Oh, that's the other thing. And then on the top and bottom pieces, I need to be able to see those pencil lines when I'm actually cutting. And since those will be down against the jig, I take a pencil and just extend those lines up the edges so I can see them. So for the jig, I have to hold the piece vertically so I can spin it around. So I needed a small dowel that I could set it on and spin it around. But the critical thing was, how far does that dowel have to be away from the edge of the jig so that this pentagon ends up at the right size? So in my 3D model, I added on the 1/4 inch piece on the bottom here, made sure it had a matching angle as well so I could see how big that piece would end up being after it was cut, and then measured the distance from the center to the edge. I think that was 0.570 inches. So that's how far back I needed to come from the cut edge of my jig. So once I had that measurement, I could then go back to the jig, measure back from the cut edge, and mark out the location of our center pin. We then took it over to the drill press, drilled a shallow hole, 1/4 inch in diameter, and then dropped in just a really short piece of 1/4 inch oak dowel. And I made sure that it didn't stick up more than a 1/4 inch from the board, because it couldn't go all the way through the MDF. It would just have to stay below the surface of the MDF. Those top and bottom plates are actually 180 degrees difference from each other. So, for example, if you look at the dodecahedron, how can I get this on camera? There we go. So here, let's look at the pentagon on the bottom here. This edge running up and down is on this side, and then if I flip it over to the bottom, the vertical edge is over on this side. So it's like I've got a pentagon here and a pentagon on the other side, but it's 180 degrees from each other. So when I stick those top and bottom plates on there, all of my lines, so when I stick the top and bottom piece on, the bottom piece, that pattern of lines, is then spun 180 degrees on the top piece, so that all my cuts end up in the right spot. And then to attach those plates, we just take this 1.5 wide, double stick tape, pretty strong stuff that I got here. Again, I'll include links to this in the description. And we cut that to the full 3-inch length of the block. Peel off the backing. Press that plate onto the block. And our dodecahedron blank is ready to go. Now that we've got our blanks all taken care of, we just need a way to secure them into the jig. Enter the toggle clamp. This is actually a self-adjusting toggle clamp that I picked up a while back, and it worked out perfectly for this project. I just needed to first lift it up to the proper height to clamp this piece in place, so I just put together a little pedestal of sorts to lift it up a bit higher. And then figured out right about where to position it so it would clamp down in the center of our piece. Marked that out in pencil. And then took the jig and just flipped it over, pre-drilled a couple of holes, and screwed it down onto the plywood. Now finally everything is in place, the jig is built, the blanks are ready. I've already worked out the method in my head and on the computer. So most of the effort went in on the planning and design side of this, and all that's left is to load up our pieces and cut out some shapes. So I've already got the table saw set to the angle that we need. Now we just drop in the jig and load up one of our blanks, and we'll center it on that hole on the pin. And just line up the first pencil mark with the pencil mark on the jig. Clamp it into place and make our first cut. After that, we rotate it to the next pencil mark, make another cut. And at this point, I've cut off some of my next pencil marks. So we gotta pop it off the jig, turn it over, and extend up some of the lines that we cut short so we can see them for our next cuts. Load it back up on the jig and continue rotating it and making the rest of our cuts. So it's 5 cuts around the bottom side, and then we end up with sort of this cone shape here. Flip the whole works over and repeat the process, matching up our pencil lines, making 5 more cuts on that side, and we're just about done. Now those sacrificial pieces on the top and bottom that we talked about earlier, those need to come off. And the double stick tape held on pretty strong. The first time I tried to take one of these off, I tried using a flathead screwdriver and really marred up the surface of the wood. Now I've seen people get dents out of wood with water and an iron, and that works pretty well. I didn't have an iron handy, but I did have my heat gun, which worked really pretty well. I took those dents and just dabbed some water on them and hit them with the heat gun and repeated that process a couple of times and took out most of the dents, and I was able to sand everything fairly smooth after that. But having learned my lesson on the first one, I came back with a knife and was able to sort of slice into the tape enough to loosen it up so I could then pry it off of the piece. Like any woodworking project, these took lots of sanding, lots of tedious little sanding, because I can't just spend my time on one big surface. I have to hit 12 different surfaces on every one of these, so it took some time to get through, but the end result turned out really nice. Because I'm just using pencil marks and not everything is super accurate, I did get a few that came out a little misshapen. You can tell the pentagons, some of the pentagons weren't quite right. They didn't look quite right because they weren't perfectly even around. But that's just from little variations in how things were rotated, and maybe we're off by a couple degrees. But for the most part, most of them turned out really well. This concludes the in-depth look at the table saw dodecahedron. Thanks for taking the time to watch, and we'll see you next time.